A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headache.
If you're building anything with AI, check them out. Modal.com. So Daniel sent us this one. And it's a question I think a lot of people building with AI agents are quietly wrestling with. He's asking what actually distinguishes one agentic harness from another, and where the real engineering creativity lives in building them. The framing is this: LangGraph, CrewAI, AutoGen, Semantic Kernel, Claude Code. They all orchestrate LLM calls with tools to accomplish multi-step tasks. But underneath, they encode radically different philosophies about how agents should think and operate. And Daniel's specific provocation is whether the future of agentic development is less about picking the framework and more about remixing your own stack of opinions on top of a flexible base. There's a lot here.
There really is. And I think the entry point that makes everything else click is a framing LangChain published in March. Agent equals model plus harness. If you're not the model, you're the harness. That's it. That's the whole thesis.
Which sounds deceptively simple.
It does, but follow the logic. The harness is every piece of code, configuration, and execution logic that isn't the model itself. System prompts, tool definitions, orchestration, state management, memory, retry strategies, context management, guardrails. Two developers using the same underlying model with different harness designs produce wildly different results. The model is increasingly the commodity. The harness is where engineering taste shows up.
And that claim about commoditization, is that actually borne out in the data?
February of this year, all three major providers, Anthropic, OpenAI, Google, hit near parity on SWE bench verified, scoring within a percentage point of each other. Sajal Sharma gave a talk at Yale where he put it bluntly, swapping models without rethinking. The harness rarely produces proportional gains. The performance ceiling you're hitting is almost never the model. It's the environment you've put the model in.
So the model is the engine, and the harness is everything else that makes the car drivable.
That's actually Evangelos Pappas' framing almost verbatim. The industry spent years arguing about who had the best engine. Almost nobody was building a car that could stay on the road.
Alright. By the way, today's script is coming to us courtesy of Claude Sonnet 4.6, which is a fun little detail given we're about to spend 25 minutes talking about agent architecture. The AI writing our podcast is itself an example of a model sitting inside someone's harness. Anyway, let's get into the frameworks, because I think the philosophy differences here are genuinely interesting and not obvious from the outside.
Right. So the way I'd frame these 5 frameworks is that each one enforces a different mental model on the developer. Not just technically, philosophically. LangGraph forces you to think in state machines. You're modeling your agent as a directed graph where nodes represent actions. LLM calls, tool executions, conditional routing, and edges define control flow. The graph supports cycles so agents can loop, retry, and self-correct. And crucially, there's built-in human-in-the-loop checkpointing. You can interrupt the graph at any node and inject human judgment.
Which sounds powerful, but also like a lot of surface area to manage.
The learning curve is real, and there's a genuine over-engineering risk for simple use cases. But the payoff is that complex multi-step tasks with explicit branching and error handling become expressible in a way that's hard to achieve otherwise. Langsmith gives you production observability on top of that.
Then CrewAI is the team dynamics one.
Team dynamics thinking, yes. Each agent has a role, a goal, and a backstory. A manager agent can delegate and coordinate. The framework encourages you to think about specialization and collaboration rather than about graph topology. What's interesting is that CrewAI's abstraction is closer to how humans naturally think about dividing work. You have a researcher, an analyst, a writer, rather than thinking about state transitions.
Though that persona-first approach presumably has costs.
A 5-agent CrewAI crew costs roughly 5 times what a single LangChain agent costs per task. The multi-agent message passing overhead is real, and for non-standard patterns, the framework opinions can feel constraining. You're paying for the abstraction in both dollars and flexibility.
AutoGen is Microsoft Research, and that's the conversation-centric one.
Conversation-centric and importantly asynchronous. Agents communicate through structured message passing. Group chat enables multi-agent discussions. What distinguishes AutoGen is that human in the loop is a first-class pattern. Humans are just another participant in the conversation, not an afterthought bolted on. Code execution sandboxing is built in, Docker and local, and the Azure ecosystem integration is deep, which matters for enterprise shops already in that stack.
Semantic Kernel is also Microsoft, right? So you have two Microsoft frameworks with pretty different philosophies.
Which is itself interesting. Semantic Kernel is enterprise first in a way AutoGen isn't. .NET and TU and Java support, dependency injection, middleware, telemetry. The mental model it enforces is skills and plugins. You define prompt templates as skills, code as plugins, and an AI-powered planner automatically decomposes complex goals into action sequences. The pitch is that you can embed AI capabilities into existing enterprise code bases without re-architecting everything.
But the planner reliability is the problem.
Complex plans can hallucinate steps. The abstraction layer is heavier than the others, and the community is smaller, which means when you hit an edge case, you're more on your own.
And then Claude Code, which is the philosophical outlier in this group.
It really is. Claude Code's approach is what I'd call simplicity thinking. The model controls the loop. The harness provides the environment. The core mechanism is a while loop. If the model produces a tool call, execute it and feed results back. If not, stop and wait for user input. No explicit termination tool, no critic pattern, no sophisticated memory system baked in.
How many tools does it actually expose?
14 total. 4 CLI tools, bash, glob, grep, lss, 6 file operations, read, write, edit, multi-edit, notebook read, and edit. 2 web tools, search and fetch. 2 control flow tools, 2 to write and task. That's it. And there's a specific reason the first tool call is almost always toto-write. The system injects the current total list after key steps specifically to fight what the lost in the middle research identified. LLMs attend strongly to the beginning and end of context but poorly to the middle. The toto list keeps the objective visible.
So the to-do list is doing real architectural work, not just being a nice feature.
It's a harness design decision masquerading as a productivity feature. And the security model is interesting too. Claude Haiku does the security checks before bash commands execute. The main model is too expensive to run on every permission decision, so Haiku gives you structured output of whether user approval is needed. Conscious speed accuracy trade-off.
I want to dig into the data that actually proves the harness matters more than the model, because there are some numbers here that are pretty striking. The Vercel case especially.
The Vercel case is the one I keep coming back to. They had a text to SQL agent, they called it DO, with 15 specialized tools. Things like get entity joins, load catalog, recall context, search schema, generate analysis plan. Very thoughtfully designed, very specific. They deleted 80% of the tools. New architecture, 2 tools. Execute command, which is bash in a Vercel sandbox, and execute SQL.
And then what happened?
Execution time dropped from 274 seconds to 77 seconds, 3.5 times faster. Success rate went from 80% to 100%. Token usage dropped 37%. Steps dropped 42%. And the worst case under the old system, 724 seconds, 145,000 tokens, 100 steps, it still failed. The new system didn't fail.
Why does that happen? Because intuitively, more specialized tools sounds like it should be better.
The mechanism is attention saturation. Each tool schema is roughly 1 to 2 kilobytes of JSON. 15 tool schemas means you're putting around 20 kilobytes of tool definitions into the context before the actual task even appears. That competes with the task tokens. The model is spending more attention choosing between tools than doing the work. General-purpose tools like Bash map directly to how models are trained. They've seen millions of Bash commands. They haven't seen your custom get entity joins schema.
So the counterintuitive design principle is strip your agent to bash plus file access, run your evil suite, see if performance improves. If it does, your specialized tools were net negative.
That's exactly the testable hypothesis. And the LangChain terminal bench experiment reinforces it from a different angle. Their coding agent scored 52.8% on terminal bench 2.0. Same model throughout, they only changed the harness. They added a build and self-verify loop, a pre-completion checklist middleware that intercepts the agent before it exits and forces a verification pass, a local context middleware that runs on agent start to map directory structure, and a loop detection middleware that tracks per file edit counts and injects a consider reconsidering your approach prompt after n edits to the same file.
The result?
66.5% move from outside the top 30 to top 5 on the leaderboard. Same model, different harness.
That's a 13.7 percentage point jump from middleware.
And the framing they used for it is good. The goal of a harness is to mold the inherently spiky intelligence of a model for tasks we care about. The model has capability that isn't reliably accessible. The harness creates the conditions under which that capability expresses consistently.
The Apex Agents benchmark from Mercor is the one that makes me slightly terrified, though.
For good reason. 480 tasks across 33 worlds simulating real professional work, investment banking, consulting, law. Average of 166 files per world. Tasks simulating 5 to 10 day client engagements. Best frontier model pass at 124%. With 8 attempts, best model climbed to around 40%. Zero score rates. Agent failed every rubric criterion, between 40 and 62% across configurations. Timeout rates, meaning exceeding 250 steps without finishing, up to 30% for some models.
And critically, these weren't knowledge failures.
The models had the information. The failures were execution and orchestration problems, agents getting lost after too many steps, looping back to failed approaches, losing track of objectives mid-task. Which is a precise description of harness failures, not model failures. The model knew what to do. The system around it didn't keep it on track.
Let's talk about Manus, because the context management story there is remarkable, and the 4 rebuilds detail is the kind of thing that sounds like hyperbole, until you understand what they were actually learning each time.
Each rebuild followed the same pattern, removing complexity that seemed necessary but was degrading performance. They removed a complex document retrieval system. They removed fancy routing logic between specialized subagents. They removed specialized tools for each operation. What they kept: file system as memory, the to-do list mechanism, a context compaction hierarchy, raw context, then compaction, then summarization, and KV cache optimization. That last one is financial. Cache tokens cost 30 cents per million tokens versus $3 per million uncached. 10 times cheaper.
And their agents average 52 calls per task, so that cost difference compounds fast.
Their input to output ratio is approximately 100 to 1, meaning context management is directly cost management. Every architectural decision about what stays in the context window is also a financial decision. Meta apparently agreed with their conclusions enough to acquire them for around $2 billion in December.
Which is a pretty strong market signal about where the value actually sits.
It is, and it connects to the broader taxonomy Sajal Sharma laid out. He distinguishes 4 layers, raw API calls, where you control everything, frameworks like LangChain and CrewAI, where you're making architectural decisions about memory, tools, and orchestration, the runtime layer, which is LangGraph, handling execution, state management and durability, and then harnesses. Claude Code, LangChain's deep agents, which are maximally opinionated. Memory, context management, agent loop, tool access, safety checks, all baked in.
And the LangChain ecosystem is interesting because it spans all 3 of those layers simultaneously. LangChain the framework, LangGraph the runtime, deep agents the harness.
Which makes it a useful lens for thinking about what the remix question actually means in practice. Because when Daniel asks whether the future is less about picking the framework and more about assembling your own stack of opinions, I think the answer is yes, and the NLAH paper from Tsinghua University is the scientific basis for why.
Walk me through that.
The paper treats harness modules as composable and ablatable objects. They ran an ablation study on SWE bench verified. File-back state added 1.6%. Evidence-backed answering added 1.6%. A verifier actually subtracted 0.8% more structure hurt. Multi-candidate search subtracted 2.4%. But self-evolution, which tightens the solve loop, added 4.8%. Dynamic orchestration added nothing.
So, more structure doesn't reliably mean better performance.
The modules that help are the ones that tighten the path from intermediate behavior to the evaluator's acceptance condition. The ones that add branching and optionality, multi-candidate search, complex verification often hurt because they add tokens and decision overhead without proportional benefit, which maps exactly to the Vercel finding. The harness components that work are the ones that keep the agent on the critical path, not the ones that give it more options.
This is where the opinionated versus unopinionated tension gets interesting to me. Because Rails made web development accessible to millions precisely by making strong choices, Next.js made React development accessible by prescribing file-based routing. The framework opinion is a feature, not a limitation, until you're the person who needs to do something the framework didn't anticipate.
The framing I find useful is Martin Fowler's. He describes the harness as a cybernetic governor. You have feed-forward controls he calls guides, agents.mendy files, coding conventions, architecture docs, things that anticipate the agent's behavior and steer it before it acts. And you have feedback controls he calls sensors, linters, test runners, AI code review, things that observe after the agent acts and help it self-correct.
And he distinguishes between computational controls and inferential controls.
Computational controls are deterministic and fast. Tests, linters, type checkers running in milliseconds. Inferential controls are slower, more expensive, non-deterministic. Semantic analysis, AI code review, but they allow semantic judgment that computational controls can't make. An opinionated harness makes choices about which controls to include, when to run them, and what to do when they fire.
And his concept of harnessability is the one that I think has the most practical implications for teams right now.
Because it creates a new category of technical debt. Not every codebase is equally amenable to harnessing. Strongly typed languages, clearly definable module boundaries, frameworks like Spring, these increase harnessability. Legacy codebases with accumulated debt face the hardest problem. The harness is most needed precisely where it's hardest to build. You could call it harness debt. And it's real.
The security service expansion is also something that doesn't get talked about enough in the framework comparison conversations.
In a workflow-based architecture, the attack surface is isolated within individual nodes. In a harness where a single orchestrating agent has access to the entire environment, file system, code execution, external APIs, a successful prompt injection has a much larger blast radius. Claude Code's Haiku-based security checks are a specific observable design response to this. Before a bash command executes, Haiku evaluates whether user approval is needed. It's not foolproof, but it's an explicit acknowledgement that the give-it-bash approach has a security surface that has to be managed architecturally.
So what does a well-crafted opinionated remix actually look like in practice? Because I think that's the question builders are actually asking when they read all of this research.
The convergence across OpenAI Codex, Claude Code, and Manus is instructive. 3 independent architectures arriving at the same principles. Fewer general-purpose tools over many specialized ones. External state management. Git, progress files, file system memory. Error retention, meaning you keep stack traces and failed approaches in context so the agent doesn't retry the same thing. Context discipline. Forward-only layers, compaction hierarchies, progressive disclosure. And extensibility via subagents or MCP rather than monolithic capability expansion.
So a remix that draws on those convergent principles would take LangGraph's state management and durability, Claude Code's minimal tool philosophy, Manus's file system as memory pattern, and LangChain's middleware hooks for loop detection and pre-completion verification.
And the Tsinghua paper gives you the ablation framework for evaluating whether each component is actually helping. You don't have to guess. You add the module, run your eval suite, measure the delta. If self-evolution adds 4.8% and multi-candidate search subtracts 2.4, you add self-evolution and skip the search expansion.
Pappas's build for deletion principle is the one that I think should be the North Star for anyone building harness components right now.
Every piece of harness logic should have an expiration date. If the next model can handle something without your scaffolding, delete the scaffolding. Man is rebuilt 4 times as models improved. LangChain's evolution from heavily abstracted chains to simpler LangGraph is another instance. The question for builders is, are you building infrastructure that gets simpler as models improve, or more complex? If your harness keeps getting more complicated as models improve, you're swimming against the current.
Which brings up the bitter lesson tension. Rich Sutton's argument from 2019 is that general methods leveraging computation always beat methods encoding human knowledge, eventually and by a large margin. A strict reading of that would predict that harness engineering itself gets obsoleted by sufficiently capable models.
Pappas has a good response to this. Multi-step execution tasks have irreducible coordination requirements, context management, state persistence, error recovery that are not reasoning problems for the model to solve, but infrastructure problems for the system to handle. The model can't fix context rot from inside the context window. It can't persist state across sessions by thinking harder. Those are environmental problems that require environmental solutions.
And Sajal Sharma's version of this is that the workflow logic doesn't disappear when you move to a harness. It moves into skills, system prompts, and tool parsing. The structure is still there. It's just expressed as instructions to the agent, and the agent decides how to apply them.
Which is a more sophisticated version of the bitter lesson than the naive harnesses will become unnecessary. Reading. The lesson isn't that scaffolding disappears, it's that the scaffolding should move toward general mechanisms and away from domain-specific handcrafting. Fewer specialized tools, more capable general tools. Less explicit routing logic, more expressive system prompts. The harness gets simpler in structure, but more powerful in what it enables.
Let's do practical takeaways, because I think there are some concrete things people can actually do with this.
The first one is run the Vercel experiment on your own agent. Whatever specialized tools you've built, strip them down to bash and file access and run your eval suite. If performance improves, your specialized tools were net negative. This is testable and cheap to try.
Second, treat your context window as a managed resource, not a landfill. The lost in the middle research is real. Models attend to the beginning and end of context, but poorly to the middle. If your important instructions are buried under intermediate results, the model is effectively ignoring them. The Tudor mechanism, context compaction, progressive disclosure. These aren't nice to haves. They're core to reliable performance at scale.
Third, build your harness with ablation in mind. Every component should be independently removable so you can measure its contribution. If you can't ablate it, you can't evaluate it. And if you can't evaluate it, you're just accumulating complexity without knowing whether it's helping.
Fourth, and this is the one I'd emphasize for teams with legacy code bases, assess your harness ability before you assess your framework. The harness is hardest to build where it's most needed. Strongly typed languages, clear module boundaries, good test coverage. These aren't just software quality indicators, they're prerequisites for effective agentic integration.
And fifth, probably the most important, design your harness to get simpler as models improve. Every piece of scaffolding you add should have a clear answer to the question, what model capability would make this unnecessary? If you can't answer that, you might be building complexity that compounds rather than simplifies.
The open question I keep coming back to is, who gets to decide what the right opinions are to bake into a harness? Rails made strong choices about MVC, and it worked for a generation of web development. But Rails also made some choices that took years to undo. An opinionated agentic harness encodes assumptions about how agents should work that might be deeply wrong for certain problem domains, and the cost of unwinding that might be higher than building from primitives in the first place.
LangChain actually published their open research questions on this, orchestrating hundreds of agents working in parallel on a shared codebase, agents that analyze their own traces to identify and fix harness level failure modes. Harnesses that dynamically assemble the right tools and context just in time for a given task instead of being pre-configured. That last one is the most interesting to me, a harness that is itself agentic about what harness it needs.
A harness that builds itself. which is either the most elegant solution or the most terrifying, depending on your disposition.
Probably both.
That's a good place to land. Thanks as always to our producer Hilbert Flemingtop for keeping everything running. Big thanks to Modal for providing the GPU credits that power this show. If you're building anything with serverless GPU workloads, check them out. This has been My Weird Prompts. If you're enjoying the show, a quick review on your podcast app goes a long way in helping us reach new listeners. We'll see you next time.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts.